Hello students, in this video we are going to study the context-free languages. Here we could see the questions from context-free grammars, Chomsky normal form, ambiguity and properties of context-free languages. Context-free grammar or type 2 grammar. Type 2 productions is of the form A to alpha, where A is a variable and alpha can be a variable or a terminal symbol. For example, S to A alpha is a type 2 production, where A is a variable and alpha is a terminal symbol. A to alpha is a type 2 production, where alpha is a terminal symbol. And all these type of productions are called type 2 productions. And a context-free grammar contains only type 2 productions. Chomsky normal form of context-free grammar. Chomsky normal form limits the number of symbols on the right side of the production into a maximum of 2 symbols. Consider the productions A to BC, where A, B, C are variables, and A to small case a, where small case a represents a terminal symbol, are in Chomsky normal form. For example, S to AS or A to SA or B, where A and S are variables and small case a and b are terminals, is in Chomsky normal form. Let G be a context-free grammar in Chomsky normal form. Then for any string W, element of the language generated by the grammar G, which has a length n greater than or equal to 1, requires 2n-1 steps to make its derivation. For example, S to AS or A to SA or B is a context-free grammar in Chomsky normal form. Then the derivation of the string BA requires 3 steps to make its derivation, where n equal to 2 here. Here we could see one particular nature of Chomsky normal form of context-free grammar. Let G be a context-free grammar without any null and unit productions. And K is the maximum number of symbols on right-hand side of any production P. Then, when we convert the grammar G into context-free grammar in Chomsky normal form, then it has a maximum of k-1 into number of productions plus number of terminals production rules. For example, S to ABA, A to AAB, and B to AC. Here, the grammar is not in Chomsky normal form. When we convert this grammar into Chomsky normal form, it has a maximum of 8 productions. A context-free grammar is said to be ambiguous if there exists at least 2 distinct derivation trees for a particular string W, which is an element in language generated by that grammar G. For example, S to ASB or SS or lambda, which is an ambiguous grammar, since for the string AABB it has 2 distinct leftmost derivations. Hence, it is an ambiguous grammar. If there exists 2 distinct rightmost derivations, then also we could say that grammar is an ambiguous grammar. Deterministic pushdown automata. A pushdown automata is a finite state machine with a temporary storage stack. The transitions are based on input symbol, current state, and stack symbol. Because it is deterministic, it has at most one move in any state, and it accepts deterministic context-free languages, which is a subset of context-free languages. Consider the DPDA for accepting the language A raised to n, B raised to n for n greater than or equal to 0. This DPDA contains Q0, Q1 as its non-accepting state, where Q0 is the start state and QF as its final accepting state. Let Z not be the initial symbol on the stack. Consider an input string A, B, B. The automation moves to Q0 itself on reading A with the stack symbol Z0 on its top. Then it pushes A to the stack. Now the top of the stack points to the symbol A. On reading the next input symbol A, it moves to Q0 state again by pushing A onto the stack. When it reads B with the stack symbol A on its top, it pops the stack symbol A and moves to the state Q1. Again, on reading the next input symbol B, it moves to Q1 itself and it pops the symbol A again on the stack. Now the stack contains only Z0. Upon reading the empty string epsilon and the stack symbol Z0 on its top, the automata moves to the final state QF, thus accepting the input string AABB. Non-deterministic pushdown automata. On an input, the NPDA can have more than one move. Consider the NPDA which has more than one move from the state Q0 on the input of epsilon empty string and the input symbol A. Hence, this DPDA can accept the empty string epsilon and the input A. Also, it can accept A raised to n, B raised to n for n greater than or equal to 0. Equivalence of NPDA and DPDA. The power of DPDA is less compared to NPDA. Hence, NPDA can accept more languages than DPDA can accept. DPDA accepts context-free languages, which is called deterministic context-free languages, which is a subset of context-free languages. All regular languages are a subset of deterministic context-free languages. Properties of context-free languages. The family of context-free languages is closed under union, concatenation, and star closure. Also, it is not closed under intersection and complementation. If L is a context-free language and R is a regular language, then L intersection R and L minus R are context-free languages. If L1 and L2 are two context-free languages, then L1 minus L2 is not necessarily a context-free one. Decidable properties of context-free languages. Given a context-free grammar G, there exists an algorithm for deciding whether L of G is empty or not. Also, there exists an algorithm for determining whether L of G is infinite or not. Hence, these two are decidable problems for context-free languages.